Good morning, everybody. Today's Codeforce's Global Round 10. Solutions at the end of the video. And also, the watching me compete might not be too interesting because I'll be doing most of it on paper, and it's rated for me. So my priority is to do well. Good luck, have fun to everyone competing, and I'll see you on the scoreboard. We have company. Pick two different adjacent numbers that are not equal and replace them with their sum. If they're all the same, the answer is itself, otherwise it's just 0. Wait, they're all positive, right? Yeah. Talk about why that's true at the end. Oh, it's 3 hours. That's new. Usually I think they're 2.5. It's being stuck at home. He became extremely bored. To pass the time, he asks Lord Akmar, 30 clock, array of n integers, also integer k. He wants you to do k operations. Set the first time matters, the second time kind of matters, but after that every 2 times doesn't matter. close at the end. Building a water slide. Wants to do it as efficiently as possible. Currently has end supports in a line. The I support is his height. He wants to build his water slide from the right to left so that his supports must be in increasing height. In contiguous subsegments. So this is 3, yeah. So I think it's just every time there's an increase, add that increase to your total. Interesting, I'll have to go back to that. So why am I wrong then? Wait, we want to make it increasing left to right? Oh, I see. Got it. So now, why do we get this wrong? Oh, they can have negative numbers. Damn, I missed that part. I didn't even read that part. Huh, alright, so... So this would be 0, (3 minus 1, 0, 2, 6. And 6. 4. 0. Oh, yeah. Yeah, that's the problem. So it's just being stupid, I think. If I didn't have that special case, it probably would have been fine even. Alright, on to D. He's playing his favorite pixelated video game. There are n players in a circle, so that for all j, from 2 to j... Yeah, okay, they're in a circle. Currently, each player is attacking each player to their left, or the player to their right. Key element is that if a player is being attacked by exactly one player, then they should logically attack that player in response. So this would be 0. This guy's attacking left. So if you ever have 3 rights in a row, right is an issue, isn't it? And you should be facing left. Okay. So you can either implement this, or implement this. So I can use 16 times n dp. dp of this one. Oh, also the first. So it's just 8n, I think. Runtime error test 3. Because I'm not reading K big enough. Man, dude, this is obnoxious. So long. Is there a better way of doing this that isn't a DP? It's like the standings, maybe? Yeah, it looks like circular DP then. And last, int 2 back, first. In position. DP at 2 back, first position, not equivalent to 1. Turn that. Otherwise, return this equals best. So They're all ones or they're all zeros, not okay, otherwise it is okay. And then, yeah, okay. So if not okay, 2 back. Okay, yeah. Alright. Can it be impossible? Yeah, it's always possible. Good. Okay, it's not okay. Otherwise, return 0. It is okay. Now, if it's okay, we need to try placing one of the two things. So, yeah. Otherwise, we get to pick. In which case, if best equals infinity, best equals math.min best. Go it back. Well, this is okay. If okay, back or 2 back 0. Additional will be our at position equals 0, 0, that's 1. Best equals math.min of the additional cost plus go of back. What I currently have, and then first position plus 1. Well, okay. We can place a 1 here. Okay, 0 if it's already 1, 1 otherwise, so 1 in this position. And then I think we're good. Okay. Alright, and then r equals mu into the right end. And then best equals max dot min, best cost at 0, 0. Let's go 0, 0, 0, 1, 1, 0, 1, this is 1. I think that's fine. Zero, 1, 1, 3, 2. Yeah, I think it's right on principle though. So runtime would be 8n, it looks like, which shouldn't be an issue. Maybe 8n times 2 or something. I don't think it's too big of a problem though. So many problems. Interactive, alright. Just came across a duck. Well, let's look at what is solved at the moment. Yeah, alright. Just keep going. The duck is walking on a grid with n rows and n columns, so that the grid contains a total of n squared cells. This is a cell in the ith row from the top, next row from the left. Initially we're at cell 1, 1. We want to reach cell NN, moving either down or right each second. Given k, exactly reproduce the duck's path. Wait, we give them the... Oh, that's wild. Darn it. Wait, did I submit to the... Problem what? From D? Oh, so it has to be identifiable what it is. Even. Got it. Alright, so now why are we wrong on D? It's right. This is left. So it only matters if these two are the same. Yeah, that's fine, I think. Oh, we care about the second, maybe? Yeah, this isn't right, though. You gotta change this to an L. I think we're fine now. Yeah. All right. Man, we're doing very poorly. Oh well. It's a long contest, so we're fine. So we want to make the top row all zeros. Might as well make the right row all zeros as well. Then we can make this element a 1. this element to 1. Maybe it's helpful to look at like the diagonals. So if we split it like that, we can just like add a big bit. Figure out where we are here. Six, 9, well it's 3 times 5, so to do the 15. Yeah, I guess that works for a 3x3. What about a 4x4? I think it takes more bits though, doesn't it? Well, how many different paths are there even? There are... choose 25? Or you go right 24 times, down 24 times. There are 28, choose 24 paths. Choose 24. Ten of the 13. So we have to do better than just random, because random would give us... We'd probably get hit by birthday paradox, I'd imagine. Well, let's read the next one, maybe. Standing at the foot of a something mountain, summit is n meters away from him, and you can see all the mountains up to the summit. So the heights are increasing. When landslide is occurring, the following occurs every minute. If the height of this plus 2 is less than the next one, then 1 square meter of dirt will fall from this one to this one. So 2, 4, 1, 1. Initially we have 0, 1, 3, 1, and this turns into 0, 2, or 1, 3, 4. This would be 0, 2, 2, 4. This will be 1, 1, 3. One, two, 3. One, 0, 1. So if you have a difference, of 2 here, then what changes? Or what if we have 2, 1, 2 maybe? So that'd be 0, 2, 3, 5. And then after one turn, it would be +1, -1, +1, -1. So that would leave us with 1, 1, 4, 4. Yeah, so the parity of each difference stays the same, so that's important. So I think we can binary search the answer. Yeah, we can do an n log n, at least. Wait. Never mind. So I should probably be focused on this one then. Well, interesting case, I guess. But not good enough. Okay, so can we maybe generate this in a smart way? If we've got this entire grid, then we can split it up like this. With one bit of information. Those are like 53. So 53, 52, 51, 50. Then let's skip 5. Well, what if we do 45, 43? It doesn't give us that many spaces. Oh, wait a minute. This is easy. So here's one bit of information. And the next one is whether you go right or down. So this is your 2, your 0, your 0. Yeah. Yeah, alright. This is easy problem. Easy problem. Alright, so doesn't use that many bits. Single test case. Looks like it, yeah. So input is first n. First they give you n. Then you get Q, okay. Alright, and then for x 0, x less than n, x plus, sys out grid x, y, plus space. We get the number of queries. This can't be an int array, this has to be a long array. Let's not make this mistake again in the same contest. doesn't equal x equals 1L left shift x. Let's make this a long just in case. Probably not necessary. But then 1, 2, 0. So long total is that. And x equals 0. Not equal to grid dot x not equal to n so now if total and 1 left shift, 1 long left shift x plus y not equal to 0. Then we need to be at an odd height. So if h mod 2 equals 0, then this is y plus plus, else x plus plus. Otherwise, we want to be at an even height. And we print it. Then we keep going. So then we print a new line between each interaction. Okay. System.out.flush. So let's say 4. My total is 5. What do you print? Oh, total's 5. 1, 1. Oh, this should be yx though. Four. Total's 5. 1, 1. 2, 1, 3, 1, 1, 1, 2, 1, 3, 1, 4, 1. That's not right. If y mod 2 equals 0, minus 1. So now if the total is say it's 3, 1 1, 2 1, 2 2. Oh, it'd have to be 3 plus 32. So 4, 3 queries. First one is 35. 1 1, 2 1, 2 2. 2 1, sorry. Then 2 2. Then 3 2, 3 3, 3 4, 4 4. I think this is right. Let's just make sure. 1 1. Well, it's a good thing to check. 4 1 3 5. Well, that could have gone better, for sure. Yeah, so it looks like F is the thing to go for at the moment. So let's do that. Well, I'm gonna go to the bathroom. I'll be right back. Alright, question 1. Does order matter? Because if not, we can make it a lot simpler. Well, instead of having all of these +1 offsets, we can like subtract 1 from everything and then add 1 back at the end. Yeah. So let's, instead of looking at this as 2, 6, 7, 8, let's look at it at 2, 5, 5, 5, I think. So then the changes to this are 3, 4, 5, 5. Then 3, well then 4, 4, 4, 4, 5. not right. What have I done wrong? 3, 4. Which corresponds to 3, 5 after the first turn. 3, 5, 7, 8. Oh, that is right. 4, 4, 4, 7. Yeah, okay. Then 4, 4, 5, 3. Four, 5, 3, 3. Two plus 2 is less than or equal to 6. Well, two, 6, 7, 8. Then 3, 5, 7, 8. And 4. Four, 5, 6, 8? Yeah, okay. Right. 4, 5, 7. Six? Yeah, this should be a 4. That's the problem. It should also be 4s. Also need a 4. You always end up like that? I think you do. You either end up with like all 4s, or you end up with like a 5 and a bunch of 4s. So it's either like n times x plus 1, or it's n times x. Interesting. If that's the case, this should have very many solves. And it doesn't. I don't know. It's a bit concerning, but we can try it. Nope. Not again. Next along minus I. Along sum. Oh wait, that's not true. That might not always be the case. This value under mod is what we care about. Yeah. So long sum equals 0 for I and A. Sum plus equals I. So long. Long array ants equals new long array n for I and 0 as less than n is plus. If I is less than sum mod n, ants at I equals 1 plus sum over n. Else ants at I equals sum over n. Yeah, I think so. Oh, plus so this is A at I plus I. Yeah. Ants at I. Okay, let's do this other case that I had drawn out somewhere. On the back side of this sheet of paper. Oh, it was right here. Got it right here. So it's 0235. So 1, 2, 3, 4. Yeah, that's right. I would lose red. Let's hope I can do better. Minus 1 is like worse for me now than it ever would be. -1 means a new color. Alright. Why is Q still backed up? We're like halfway through contest. Come on. What is going on? Oh, it's not that backed up. Alright, we got it. 56th place isn't bad. It's not bad. We're worse of everyone for the people that have this number of problems because they have so many wrong answers, but not the end of the world. All right, so let's gather our bearings. So okay, there are 3 problems left, which are all challenging. Who is good at them? Andrew He and William Lynn and Tourist are good at them. How do I feel about that? I don't know how I feel about that. I wouldn't say that excites me. Ben Q is not easily good at them, neither is Kusaga. Ooh, this could be a rough set. Looking a little bit rough at the moment. That's not good. Well, I didn't have a good start either, so that's fine. Alright, so the question is, we've got an hour and a half left. We gotta get one of these. That's the goal. So let's read at least G and H. And then I, if it's not geometry, I don't know if it's worth doing. If I has a geometry problem... Oof. Yeah, I don't know. Maybe, let's read, if Andrew can get both G and H, we should be able to read them at least and understand what's going on. Then maybe after that we can do something better. He's got a tray with up to 20 spots. Each spot contains either a chocolate pie or a pumpkin pie. However, he doesn't like the way the pies are currently arranged and has another ideal arrangement that he would prefer instead. To assist him, N elves have gathered in a line to swap pies on his tray. The Jth elf from the left is able to swap pies at position A and B. In order to get close to his ideal arrangement as possible, he may choose a continuous subsegment of elves and pass the pie tray through the subsegment starting from the left. So you take some continuous range of swaps. You also have to swap at least M elves. Help him choose some subsegment of elves so the amount of positions in his final arrangement of the same type is maximum possible. It might be that the amounts of each type of pie... Wait, what? The number of positions which match is maximum possible. The amounts of each type of pie in his original arrangement and his ideal arrangement might not match. Oh, it's a binary string. Got it. So you swap 1 and 5, basically. Then you get 4 things to match. Oh wait, you swap 1 and 5 and 2 and 4, so you get 5 to match. Alright, I think I understand the problem. I don't really have any ideas immediately. Problem H. You've got a deck of n plus m custom cards, in which consists of n cards labeled 1 to n and m jokers. Initially, the deck is shuffled uniformly, randomly, and placed on the table. You've got a set which is initially empty. Each second, you draw the top card from the deck. If the card has number X written on it, you remove the card and add X to your set. Oh, there are jokers too? Yeah, M jokers, got it. Okay. As a joker, you place all cards back into the deck and reshuffle to form a new deck. So there's no difference between just well, there's a difference, which is you have several cards. Well, for this one, I can see where like an n squared DP might come from pretty easily. For G, I kind of have no idea. Like, maybe it seems like you do a 2 to the n on this. Like, you brute force which things wind up being correct. So now you know what your final arrangement is. You just want to see, like, is this possible to make? This one's also very math heavy. This is not the kind of stuff I'm good at. This is the kind of stuff that, like, I don't know, Eric does good at. Stuff that's like classic Chinese high school problem. Maybe I'll try it anyway, though. Alright, so we could do like a DP for the number of cards in our set. Because which cards they are don't matter, because every card is pretty much just the same. DP at n cards. Initially, we'll just do a slow transition, but then we'll figure out how to optimize that in a bit. So either well, I suppose really it's DP of the number of cards and also whatever m is, right? Number of cards, number of jokers. So then we have a n over n plus m chance of getting a new card. We have an m over n plus m chance of getting a joker. So the new card would just be DP n cards minus 1 by n jokers. What's the chance we get a joker? Well, it's that. Then the expected payout for the joker is weird because then our DPS cycles, so we have to do math in order to fix that. Oh, but the number of jokers is always constant. Yeah, you always have m jokers. Oh, so we just care about what's the expected number of jokers you'll pick. No, not the expected number of jokers, the expected number of cards you'll pick. Like, yeah, you just care about the expected number of draws. And that's like a tricky thing to do because the number of cards you don't care about is not constant. The irrelevant cards matter. Wait a minute, did I see a cyan here? Is this guy really just popping off, or is he an alt? Definitely an alt, 100% an alt. Stop cheating. Okay, well... yeah, it'd be very nice to solve one of these problems. Let's look at this one, maybe. Because, like, this one's gonna get... F is gonna get a whole bunch of solves, because it's really easy. So it's just a matter of time before a bunch of people beat me, because I have bad penalty. So it's really important to actually get one of these. If we get one of them, that should be fine. Like, they're hard enough that I think that's fine. So say we know, yeah, let's pause this for a minute. Say we know how many, or which cards are going to be completed. Well, if every node has an even degree, or if every node has the same in degree as out degree, if we make this into a bunch of nodes, does that help us? If every node has the same in degree as out degree, that means every time you enter a node, you also leave the node. So it's the same as doing nothing, I think. Is that even true? If we have this 1, 2, 3. Then we have the C, D. It doesn't actually stay the same. Wait, maybe I'm misunderstanding the problem. What does this mean? The amount of each type of pi in his original arrangement, his ideal arrangement, do not match. How does that happen? Since he has a big imagination, the amount of each type of pi in his original arrangement. Oh, I see. So you might have like too many ones, so you can't you might not be able to do it perfectly. I see. Well, we can do any continuous range very quickly in log n time. Actually, it's a permutation, right? So we can do it in... We can do it in 20 squared. We can do it in order 400. Yeah, we can do it in either log n time. I guess n times log n. K times log n. I see. I think the hard part is that there are both left and right endpoints. Like if n were 1,000, we could do it. Because you're just composing two permutations. So if you do one permutation, then you do another. Doesn't change by much. Yeah, we can do it either with matrix expo, on like a segment tree, or, ooh, I guess that would be log matrix multiplies. Maybe log matrix multiplies is not a good idea. So maybe in a different way, you have a bunch of these operations. You might want to swap these two. Oh, I think I see where this might be going. You might be able to, like, do one operation, because you know both the starting and ending points. You can do, like, kind of a meet in the middle. So you do one thing from the left with, like, one of the arrays, one thing from the right with one of the arrays. And now you're like, alright, of all of the ones that exist, which one is best for this? Might be 3 to the K, though. Because updating a bunch of things is tough. Oh, do we want max over subset? So maybe we do all of these permutations. But first we did this inverse permutation. So yeah, you can undo permutations just like you can undo addition. That'll leave us with this range here. We do some number of permutations, and we invert them. Okay, so now doing some swap on the original is the same as doing the swap on the final. So doing this range of swaps is, I guess, the same as doing all of the swaps and undoing these ones first. This max flow, maybe? Min cut? I'm gonna see what's the minimum difference between two things. That would be really cool. Kinda doubt it. Because bounds are huge. Oh, we can just, instead of undoing these, we can just do those to our answer as well. Yeah, that's an easier way of implementing it. So do these to the answer, and these to like the start. So now we're at the sub-problem, which is I've got a bunch of masks, and I want to quickly find which one is closest to what I'm currently at. Like, very quickly. Sounds like a difficult thing to do, to be honest. Maybe it's just a BFS. BFS might be quite slow, though. Yeah. You could try BFS changing at most 10 positions. Maybe the BFS is fine. Because once you've like added a bunch of masks. Yeah, if you update a position, you decrease it. That can only happen log n times, right? Because the distance to anything is at most log. Yeah, okay. Alright, so that's the solution idea. So what do we do? So we've got a bunch of these permutations. We're going to do these things to the start, these things to the answer. Oh wait, we have a problem. Yeah, no, that's fine. It's easy to handle. Okay, so the idea is like brute force the start. Then keep track of distance from start, from any start. No, from this. What are we trying to do? Yeah, keep track of distance from any answer to the current start. Because we're only adding answers. The distance to any answer from this current start. Well, the distance to any answer from any position. From everywhere. Then when we add an answer, then we like continue our BFS. Yeah, okay. So it shouldn't be too bad, I don't think. Let's do that. You know the contest isn't going poorly when you're out of things to type, like when you're out of problems in your default template. Okay, so n this thing. I guess n swaps. Min swaps is this, and then what is k? Yeah, n bits. So int start mask plus equals line 1 at I minus the character 0 left shifted by I. So we have this start mask and the end mask. So well, okay, I guess int per d, what do we need? Array deck integer BFS dist from is equal to 0, then return. Otherwise, dist from equals 0. BFS dot add last. From. So change each bit. The other one will be where it'll be next XOR 1 left shift change. If distant other is greater than distant next plus 1, then distant other equals dist next plus 1, dfs dot add last other. What do you want to print? The most it can be? Oh, also the range, okay. Ants range equals -1, -1, or ants start equals -1. Ants end is 1. Sys out and bits minus ants. Sys out and start plus. L equals new int array and swaps are swaps. And we have to read these in. So read in the left and right endpoint for each of these positions. All right. Now, int I equals 0, I is less than min swaps. Otherwise, return mask and 1 left shift. Max XOR 1 left shift I, XOR 1 left shift J. So flip this bit, flip that bit. Okay. Swap, I guess start mask, or what are we doing? Yeah, start mask equals swap, start mask. L at I and R at I. So while I plus min swaps is less than n. Gotta be careful with my off by ones here. Is less than n swaps. End mask equals swap end mask L at I with R at I. BFS from the end mask to where do we go to? Oh, for the current distance. Then swap them. And now, now we have to swap the start as well. Yeah, so now start mask equals swap start mask L at I plus min swaps R at I plus min swaps. Almost. Okay. Canned would be oh, we also need where it comes from. If there are multiple answers, print any, right? Good. So that was negative ones. All right. Come from I. So if the distance to the start mask is less than the answer, then that means ans equals dist start mask, and start equals came from start mask, ants end equals I plus min swaps. All right, so we have a couple issues here. So this just needs to be a while loop. While Ri minus Li plus 1 is less than min swaps. This is just, well, that's our right index, this is our right index, and its end will be the right index. Left index plus plus. These are both the left index. This is just, well, the right index is less than the number of swaps. So come from the left index. BFS from the end mask, distance to everything, the distance or where each thing comes from, and coming from the current left index. If it's a new best, store it, otherwise increment your left index. Also increment your right index. So this should be right. These need to be one based though. I didn't copy this one, right? Oh, yeah. So this should be fine, I think, right? Start mask. Let's do this on paper, see if this is even right. Initially, it is 1, 1, 0, 0, 0 is the end, and the start is 0, 0, 0, 1, 1. We need to include at least two things. So this RI is not shouldn't be at 0. Should be at -1. Ri plus 1 should be Ri plus 1. Should also be Ri plus 1 and Ri plus 1. Okay, I believe it. Three, 1, 3. 1, 2, 3. That is at least 3 things, right? Let's try it. So initially you have 1, 0, or 1, 1, 0, 0, 0. You want to go to 0, 0, 0, 1, 1. So you swap 1, 3. Then you have 0, 1, 1, 0, 0. Then you swap 1, 5, which doesn't do anything. Then you swap 2 and 4. So then you get your 0, 0, 1, 1, 0, which matches in 3 places. You can also, we could do less than or equal to min swaps. Nope. We want less than or equal to answer. Then we should get the answer they're looking for. 1, 4. Also make sure this one's right. 5, 1, 3. Yeah, okay. So I think this is fine. Let's submit this. I'm gonna have to write my own array deck. The TLUs. It should be pretty fast, I think. I'm gonna go to the bathroom. We'll be right back.
Problem due by real-time error test answer.
I heard runtime error test 5, which is very interesting because I have no idea what could possibly runtime error. But thankfully we should have enough time to debug. It's not that I'm reading in ints again, right? Yeah, everything should be small enough, I think. Read in the number of bits. There's gonna be something stupid, I can feel it. Can it be 0? No, it's at least 1. Wait a minute. Hold on a minute, what? This wasn't even right. It starts at 0, which means we have to do the 0 with swap first. It's kind of surprising how well that did, though. Passed 4 cases without even being close. Yeah, that definitely needs to be here.
Problem due back normal for test 6.
Darn it. Yeah, we can definitely get G. Shouldn't be too bad. H has quite a few solves, by my friends at least. Alright. Let's figure out why this is wrong. Well, okay, first question, we have 30 minutes, can we write a brute forcer? What does a brute forcer entail? Generating random data is easy. The naive is just trial pairs. Yeah, just 10 cubed. Okay. So that's what we're gonna do. Then we'll have a break case. Okay, int n bits, or n swaps, equals 1 plus r dot next int 5. Int n swaps equals 1 plus r dot next int swaps. Int n bits equals 1 plus r dot next int 3. Binary string of length n bits. Twice. Int a equals, can these be the same thing? 1 plus r dot next int bits. Well, okay. Well, okay, so that's that. Now we need our brute forcer. And swaps equals this, and swaps equals this, and this equals this. For in start equals 0, start is less than n. Swaps start plus plus, for end equals start plus min swaps minus 1, end is less than min swaps plus plus. And cur mask equals start mask. Start, end. Okay, so if cur mask and 1 left shift I is different from the end mask and 1 left shift I, then diff plus plus, best equals math.min, best in the diff. Equals then diff plus plus math.max. Okay, so run the generator code, get this stuff. Run this. Here are the answers. Two, 1, 2, 3. Well, it's just. Alright, so we've got this. Print it to the file. Close. We also want a different file. We want to judge that out. Documents. GitHub, or yeah, CodeForces here. They are different. Okay, let's do just 10 cases maybe. One case. So let's see, can we make it smaller? Swaps, let's just do 3 swaps. Or maybe 4 swaps. Well, 3 swaps would be nice. Plus 2 third cases. Wait, what? Oh, this is the gen. Yeah. Okay. Case 27. If PT equals 27, so here's the one case that matters. So we say the answer is 2. But the answer isn't 2. The answer is what? What? Okay, that is a different case, which is odd. But that's fine. Alright, 15 minutes left to fix this case. We say the answer is 3. In reality, the answer is 1. You can swap 3 and 2. You swap 3 and 2, then 1 and 3. Yeah, okay, interesting. So we're just wrong here. What's the idea? We swap oh man, is this undoing not work? Yeah, okay. So you can't just do the same permutation to the answer. That doesn't... The prefix of the permutation to the answer doesn't actually work. Instead... we've got a bunch of things. We want to look at some... Oh man, that's really annoying. That's like the worst thing that could have gone wrong, because that's hard to debug. Huh, darn. So that doesn't work. It's very annoying. Yeah. Can we decompose this into an operation in the beginning and an operation in the end? Why couldn't we? Well, I suppose the reason we couldn't is because we can't... We do all of these. It would have to be... We have to... Yeah, we have to go like this here. We have to do this part. Oh, is it... Do I have the beginning and the end backwards, maybe? Is that it? So we need to do some of these, we need to do all of these swaps from the start. So like start to do these. Oh, the end needs to do... That's kind of weird. Yeah. Okay, so we can fix this though. How much time do we have? 7 minutes? Maybe. Maybe we can fix this. So now the end does these swaps. These are from the end. These are from the start. So that would add this. Okay, so, well, can we make it simpler? Yeah, okay, we care about the permutation of the things in the end. Yeah, okay. So interarray, this is really the add to end. So we've got the end perm equals new interarray n, or n bits. End perm at I equals I. Now static int add to end perm. Int I j interarray perm. here, then j index equals k. Yeah, so now perm at j and I, perm at I equals j. This is just void. So now this is add and perm these things right here. Okay, this is the same thing goes here. Now static void get end mask into given end mask into a perm. For well, Boolean array n equals new Boolean array and bits zero as with an n bits plus if given end mask and one left shift I equal to 0, now equal to 0, and end at perm I equals true. Okay, this is int end mask equals get end mask, end mask, and perm, and bits. No! Well, let's just test samples then even. Compilation error. Five. Well, I'm really close. I'm really close. Ah, man. It's unfortunate. I went up a little bit. Could have gone up a lot. I was so close. Man, I was so, oof, almost there. Yeah, I don't know. It's hard to, you can always say if I would have done this, if I would have done that, but like, if I'm infinitely smart, then I would just solve all the problems instantly, right? So there needs to be some allowance for the fact that I'm going to make mistakes in a contest, and if my strategy relies on me not making any mistakes, it's a bad strategy. But I don't know. I feel like this was pretty unlucky. I feel like I was very, very close. I'm pretty sure this is the right idea. I just have like a very small bug I have to get somewhere. But yeah, well, let's see. How'd my friends do? Eric got it. Nice job. Nice job, Andrew. 3rd place. That's not bad, not bad. Tourist, a little unfortunate. 4th place is quite good, but if you're tourist, you know. yeah, looks like I was pretty tough. This one wasn't as bad. I don't know. Maybe it's like it seems like it's some sort of DP, and then you do some math in order to speed it up. I'm not sure. Spencer Compton. Yeah. All right. Well, nothing too crazy. Did Monaghan do it? Monaghan didn't. I wonder what he was doing. Maybe he was a tester or something. All right. Well, anyway, let's go over solution details. How about that? So, yeah, I thought. Well, actually, maybe let's talk about the problems first, like what I thought about them. Let me just, let's just bring up the complete problem set, and then people have been telling me to do middle click here, and I've just, it's just force of habit, right click and then left click. Alright, so this password one, this was a cool problem. I liked it. This was like, as far as problem A's go, I think this is like the best it gets. Because there's a really, it's like cool to prove. You feel smart when you solve it. Yeah, overall, it's just like a good, very good problem. So I was a big fan of problem A. This infinity clock, yeah, I thought it was cool too. Yeah, it's quite cool actually. I really like it. I struggled a lot with it. I had like 2 wrong answers for stupid reasons, but I think it was a really cool problem still. This water slide one, I guess it was easy. Yeah, it was really easy. It's pretty good, I guess. I liked it. Like, no hard comments about it. I think, for the most part, like, a lot of people took longer on this than they should have for it being as easy of a... Like, this was, I thought, at least about as easy as problem A. So I don't know why it took people so long. But oh well. What is this Bed Wars one? Oh, yeah, this one, this was pretty classic. Like, this is just the classic sort of circular DP idea, where you care about what happens in the beginning. So, not a bad problem. It's pretty normal, I guess. Nothing much to say about it. This was a cool problem, the stuck problem. I liked it. It took me longer than it should have to figure out, but it was still like a cool idea. So I'm a fan of that one. There were lots of problems. F... Yeah, it was pretty easy, I guess, in hindsight. Like, for me at least, all of the observations you had to make were very straightforward. It was like, here's this, that's not a hard observation, it's not a hard leap. Then the next thing also wasn't a hard leap. And then once you've made all the observations, it's pretty clear what the answer is. So it's just like, simplify it, and then don't be an idiot. It's Pi 1. Honestly, yeah, I liked pretty much all the problems. This one was a good one too. It's a little hard to wrap your head around, I think, the solution. Maybe that's just me. Maybe for other people, it's not as bad. It was cool. It's good. This one, yeah, I don't know. I don't really know about it. Like, I don't know the solution, so I can't commentate on whether it's a cool solution or not, because I don't know. This one I didn't even read. It was too hard. So yeah, good set. Good set. Let's talk about these solutions now. I have no idea how much that fan hurts the audio. Like, I try and keep it lower when possible, but otherwise, like, it gets really hot. Okay. So, solutions to the problems. Starting with problem A. So, in problem A, you have this, like, I don't know what the password has anything to do with it, but basically you have some array, and on every turn you can pick 2 numbers that aren't the same and add them together, and then replace both of those numbers with just the sum of the numbers. So obviously, if all of the numbers are the same, you can't do any operations. So the array you're going to be finished with will just be that final array. Otherwise, if all the numbers aren't the same, that means there's some number that is different from the rest of them. Whatever that number is, we can like consider it alongside whatever number is biggest. So maybe the array is like 4, 7, 10, 10, 10, 3 or something. We'll take whatever one of these like maximum numbers there are, we'll take this and then match it with some other number. We know since the array isn't all 10s in this case, there will be some number next to a 10 that's not equal to a 10. After we do this, we now have a 17 here. This is the strictly biggest number. We can just match this with everything else, and that's the solution. All right, so that's problem A. Pretty easy. I'll show you the code for that. Let's just check if they're all the same. If they are, the answer is n, otherwise it's 1. Problem B is about an infinity clock, and it's a neat problem. So basically, you have one operation you can do. That operation is you find the maximum of all the elements in the array, and then you set every value in the array to be the maximum minus what its current value is. So here's the idea for that. Let's say your values are like 3. I'll draw them in decreasing order because I think that makes it easier to think about. So 3, 1, -5, -10, for instance. So first we find the biggest number in the array. That's this 3. And we like shift everything down by, or we shift everything to like its distance from 3. So the 3 turns into a 0. Then this turns into a 2. This turns into a 8. And this turns into a 13. Now, here's the important thing to notice. After we've done this, the smallest number in the array is going to be this 0. We can't have anything that's negative because everything is going to be smaller than the biggest number. So now this smallest number is 0, which means when we do this operation a second time, this 0 will turn into whatever this biggest number is, which is 13. The 2 will turn into 11. Then the 8 turns into 5. 13 turns into 0. So now the thing to notice is, if we keep doing this operation, we'll just switch between these two arrays back and forth. So we know k is at least 1, so we can do this once just like naively in linear time. And then we just care about the value of k minus 1 mod 2. So what does that look like in code? I subtract 1 from k right here, because you know it's positive. Then you don't actually need this part. You can just do this code. This should be fine. And you do this operation that they tell you. You do it k mod 2 times. That's what matters. Okay, so that's problem B. You have to make sure you read in longs, because k can be bigger than 10 to the 9, so be careful about that. And then also just don't be an idiot like I was the first time. And then it should be pretty easy to get right. Okay, problem C. So you're trying to build this water slide, and you can add a constant to some continuous range. And the goal is for you to add, or for you to make the water slide be like non-decreasing, so like increasing or stay the same as you go to the right, and as few additions as possible. So here's the idea behind that. Let's say your water slide looks like 3, 5, -2. No, not -2. 3, 5, 3, 4, 7 maybe. So what we can do is if we add to some continuous range, maybe we choose to add to this range here. So after that we would have 3, 5, 4, 5, 7. And then after that we could add to this range here. So that then we have 3, 5, 5, 5, 7. So that's like what we're trying to achieve. But let's look at this in a slightly different way. Instead of looking at the actual values, let's look at the differences between adjacent values. So the difference array would be like, initially it goes from 0 to 3. This is a +3. Then we have a +2. Let's look at the original array, actually. So +3, +2. Now we have a -2. We go down by 2. +1, +3, And then this one doesn't really matter. There's not really anything here. When we do this range add, what happens is we add 1 to this number, and then we subtract 1 from this number. So that's really the operation we're doing. If we look at the differences array, we add 1 to one number, subtract 1 to some other number. That's like really just what the operation is. We can also choose to not subtract 1 from any number if we have this range go to the end of the array. So the goal here is to make all of the numbers 0 or positive. The best way of doing that is to only add 1 to certain numbers that are negative, and then not subtract 1 from anything by just having this range go to the end of the array. So basically, yeah, that's it. So we just look at this array, and every time we have some negative number, we're going to have to start a range there, whatever that number is, like that number of times. So we just look at this difference array. Every time we have a negative, we just add the opposite of that negative to our answer. That's the total. Okay, so that's problem C. Let's look at problem D. We've got these bed wars. So yeah, this is a common idea. It shows up quite a bit, but it's not particularly easy, I guess. It's not super obvious, at least. So here's the main idea. When the question is like, when do people not play optimally? So if you have the person to your left, if they're going to shoot you, and then the person to your right isn't going to shoot you, then the only time you're not playing optimally is if you also shoot to the right. So if you have like a right, 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 that's not optimal. And then if you have a left, 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 that's also not optimal. Those are the two things you can't have. Of course, it's circular, so you also can't, like if you have some circle, if you say this is where you start, you can't have a right here and then also start with 2 rights and a left, for instance. That's not allowed. So to me at least, it's possible there's a greedy, but to me at least it isn't obvious what that greedy would be, because it's not super clear to me how you want to change these numbers, or change these rights and lefts. If you have 3 rights in a row, you're going to have to change one of them, but which one you want to change, to me, isn't obvious. Like, it's possible you have a bunch more rights here, so you want to change this one. But it's possible after this right, you have 2 lefts. So you don't want to make this a left, because if you did, then you'd have to make one of these a right, so it'd be an extra move. So maybe you can case work it out and figure out what you want to do. Maybe there's a greedy, maybe not. But you can definitely do a DP. And the DP isn't actually too bad. So here's the idea behind what that is. Let's say we brute force what these first 2 elements are. We know whether they're a 0 or a 1. There are only 4 different possibilities for that, so that's pretty easy. Then after that, we can do some DP, where what we care about is what position are we on here, and also what are the last 2 values. So that's the DP. The runtime of that so far is going to be n times 2 times 2. So what we can do here is we can either make this a 0 or make it a 1, but we can't do one of those options if it creates 3 things in a row that are all the same. I guess you also have a transition of 2. Okay, very good. However, there's a case that this misses, which is we're forgetting this is circular. So we also aren't allowed to have these 3 be the same. And also, I forgot this was my wrong answer, we're also not allowed to have these 3 be the same. So we also, in addition to caring about what the thing 1 before us and 2 before us is, we also care about the first thing in the array and the second thing. So we also need to store 2 more factors of 2 in our state. So our state will be dp of like what's 1 behind you, what is the value that's 2 behind you, and then also what is like the first thing in the array. Also, what is the value that's second in the array? And finally, what position are you at? Then you have a transition of 2. So the final runtime is 2 to the 5th times n, which is equal to 32n, which should be fast enough. It's pretty much n log n, right? Not that bad. Uses 2 to the 4th times n memory. Okay, that's the solution. I'll show you my code for that. I think I forgot to show code for C, but it's very easy. That's it. That's code for C. For D, yeah, so this brute forces the first 4 elements. And then this cost just figures out what's the cost of making the first thing this, second thing this. Saves some casework for me. The DP is pretty simple. Basically, if the position is n, you have to make sure the 2 ranges that I talked about are legal. If they are, then you return 0, but if one of them isn't, you return infinity, so that you don't actually do this. Otherwise, you do one of these 2 cases. So if it's okay for you to place a 0 here, if that doesn't make 3 zeros in a row, then you place a 0 and you do that. Otherwise, you place a 1. The transitions are just, these are like back and 2 back, or what's 2 behind you, what's 1 behind you. So move those back by 1, and then place this new thing here. And then your position gets incremented by 1. The first and second things stay the same. All right, cool. So that is problem D. We'll look at problem E as well. We'll look at E, F, and also G. So we've got quite a few left. There are just lots of problems, which is why this video is going to be longer, but that's fine. All right, for problem E, you have this interactive problem, and basically what it is you give them some grid, then they're going to find some path in the grid that only goes right and down. You have to tell them what that path is, only given the sum of the values along the path. So, how do you do it? Well, all right, there's a couple things to notice. This is like a really common idea with the only go down and right. It shows up quite a bit. So it's important to know. Which is, you're only gonna, like, you'll visit this top left corner, but you're only gonna visit one element in this diagonal here. Yeah, okay, that's fine. You'll only visit one element in this diagonal here. You only visit one in this diagonal here. Then I'll just cycle my colors, but you get the idea. It's got to be square. There you go. So there's like each colored diagonal, you only visit one element in it. Now, what we have to determine is, like, when you're at some given space, let's say you're here. On the next turn, you might go right or you might go down. That decision matters. Also, if this is like, what turn will it be when you're here? Well, it'll be the it'll be the third turn, right? So on the first turn, you go right, maybe. Second turn, you go right. Third turn, you go right. Now, I guess, okay, so this is the fourth turn. On the fourth turn, what decision you make is whether you want to go here or here. The idea is, if we're going to figure out whether you went right or down at each position in this path, we want to know, like, we want some differentiating thing between these 2 nodes. We have to be able to tell the difference between them, basically. Because if you went right and then went down, we have to be able to tell the difference between these 2 paths. So what we can do is, let's say we know whether you visited this red node or this red node here. Then for the blue nodes, we care about, did you visit this blue node here, or this second blue node, or this blue node? Now, we don't need to be able to distinguish between these 2 blue nodes. You can't visit both of them. And we'll already know whether you're at one of these 2 red nodes. So imagine we already know that. Now, if we say, okay, you visited one of the nodes that I've colored in with stars, then that means if you were at this top red node, that means you went right. If you're at this red node, that means you went down. So we can color those in like that. Then the green ones we can color in like this in a similar way. And then the white ones we can color in every other row again. And the idea is that we are ultimately going to color in this top row, this middle row, and this bottom row. Now, when I say color in, I mean these need to be distinguishable in the total. So we'll make each of these a different power of 2. Each column will have a different power of 2. So the total number of powers of 2 that we'll use will be n plus n minus 1. Or I guess it'll be n minus 1 times 2, really. It's kind of weird writing in the stars. It's hard to see. But yeah, this is the total number of the biggest number in the array will be that. And yeah, that's the idea. So basically, you can like figure out for a given step whether after that step you were on an odd height or an even height. Given that information, you can figure out whether you walked right or down. And that's the idea. The code for that is pretty simple. The grid is just going to be, if it's an odd height, then you put a 1 there. Otherwise, you put a 0 there. And then when you're given the total, you can extract the path by looking at each step. Now, for each step, you just want to say, okay, should I be at an odd height after taking the step or not? If you should, you make sure you're at an odd height. So if you are currently at an odd height, then you walk horizontally. If you're at an even height, you walk vertically in order to make it to an odd height. Otherwise, you do the same thing with an even height, just backwards. All right, it's problem E. Problem F. Keep her moving. Akmar and landslide. Yeah, okay, this one was a cool problem as well. So let's talk about it. So the idea behind this one is let's just make a bunch of simplifications and see where it leads us. So the problem is you've got some array. I'll do the first sample, 2, 6, 7, 8. It's a pretty good example, I think. Every time you're gonna like do this repeatedly until the array doesn't change. Every time you have two adjacent numbers that differ by 2 or more, you subtract 1 from here, add 1 to here. So after we do this step, it would be 3, 4, 7, 8. In this pair, this is the only time that happens. None of the other numbers change. So this is like, the difference is like greater than or equal to 2. All right, so now after we do this, then let's look at this step here. After we do this first step, then this difference is 2 or more. So then we have 3, 5, 6, because we add 1 here, subtract 1 here, and then this 8 stays the same. So now in this next step, 2 things happen. We add 1 here, and we add 1 here. So it would be 4, 4. Wait, is this right? I guess so. 4, 4, 7, 7. Yeah, I think this winds up working, maybe. It's possible I made a mistake, but it's not too important. Then after this, we have a big difference here, so we add 1 here, subtract 1 here. So now it's 4, 5, 6, 7. So I did make a mistake somewhere, which is... I don't know, I made some mistake. One of these numbers is smaller than it should be. Yeah, doesn't really matter. But, yeah. Like, so, this isn't the right answer. I did the simulation wrong, slightly. But the mistake I made isn't super important, so we'll just pretend I didn't make it, and then maybe we'll find it later. So there are a couple things to notice. The first one is we can, like, kind of imagine subtracting 1 from this position, subtracting 2 from this position, subtracting 3 from this position. I think that makes the problem easier to think about. If we do that, now instead of the constraint being the adjacent difference has to be 2 or more, it's just these numbers have to be 1 or more apart. In other words, every time you have a number where it's like if you have like a 3 and then a 4 and then a 3, for instance, when you have this, you modify it by adding 1 here, subtracting 1 here. So if we've transformed the problem by changing these numbers in this way, now we can imagine everything will flood to the left. So if we have 3, 4, 3, this changes into 4, 3, 3. Really what this would turn into in this example would be 4, 3, 3, or 4, 4, 4, 4, right? Because if we subtract 1 from this, subtract 2 from this, subtract 3 from this, we have this new array. We can really easily convert back by just adding 1 here, adding 2 here, and adding 3 here. So yeah, so if we look at the simplified version of the problem, if we have this 3, 4, 3, it turns into something like this. What if we have a 3, 3, 7, for instance? Well, then we'll add 1 here, subtract 1 here. So then we have 3, 4, 6. Then we'll do the same thing again. So now we'll add 1 here, subtract 1 here, add 1 here, subtract 1 here. So now we have 4, 4, 5. Now we add 1 here, subtract 1 here. So we have 4, 5, 4. Finally, we would have 5, 4, 4. So in other words, the values just cascade to the front. That's the change that happens. It's pretty easy to figure out what these will be with math. So the invariant is the sum of all the numbers never changes. And also everything becomes as equal as possible. Since we know that initially this value, or this array is sorted. We're promised that initially. So since we know it's sorted, we know things will slowly cascade to the front. And in the end, you'll have a bunch of numbers. So you'll have like x, 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 and then maybe x minus 1, x minus 1, x minus 1. And like that's what your final array is going to look like. So we just have to figure out what this is. We know the number of x's here. Like let's say there are n things total. The number of these that are x will be equal to the sum modulo n. The remainder of the sum when you divide it by n. Then these things will all be the same. The rest of them will be 1 less than that. And then the value of this will just be the sum divided by n floored. So again, super easy to code. Here's what that looks like. What problem is this? Problem F. Super easy to code, just a few lines. And like once you have this, finally you have to transform it back. So yeah, there's that. Okay, so yeah, that's problem F. Finally, let's talk about problem G. And I think I have the solution to this, but yeah, it's not too bad. All right, so how do you do problem G? So I don't have code to show you guys because it's not completed yet, or it still has at least one bug in it. But here's the main idea. Or here's the problem first. So you have a bunch of positions, like you have some binary number, and it goes up to 2 to the 20, and you want to change it into some other binary number. You also have a bunch of elves. Each elf will switch the value in 2 binary positions, so to like swap these 2 bits basically. Now, what you want to do is you want to pick some consecutive range of elves where you pick at least like some minimum number m. You want to pick at least m of them and do all of their swaps in a row. And then you want to end up with some other number where as many bits as possible match what your target goal is. That's the idea. So here's the solution path to it. Basically, you have all of these events, right? The idea is when you have some binary number, there are 2 to the 20 binary numbers total. The maximum distance from some number to any other number will be 20. At most, we have to change every bit. That's the worst it can be. So if we want to find the number of bits that are similar, we want to like, so let's say we have some number, we have like this 0, 0, 0, 0, 0 or whatever, and we want to reach some other number 0, 1, 1, 0, 0, 1. The distance between these 2 numbers, if we have a graph, like let's say we make a graph where each node is some binary number, and all of the edges are, if they differ by 1, we have an edge between them. So in this case, we wouldn't have an edge between these 2 directly. We would have an edge to something else, right? So maybe we have an edge to 0, 0, 0, 0. These aren't even the same number of bits. We have an edge to that, which has an edge to 0, 0, 1, 0, 0, 1, which has an edge to this here. So the distance between these 2 numbers, like this number 1 here and this number 2 here, or I guess we'll call them A and B, is 3. We have to take 3 different edges, which means there are 3 bits that are different. We're trying to minimize the number of bits that are different. That's an easy enough thing to do. Okay. So if we imagine we have some like minimum path from some node to every other node, if we like repeatedly add new sources to our BFS, the total number of times that will update the distance to any node will be 2 to the 20 times 20. Because the maximum distance to any node is 20, right? If we have some array of like what's your distance from any start node, which we'll get into where these start nodes come from in a bit. But if you try and come from any start node, you want to know the shortest path from any start node to this end node. That value is at most 20. And when you do your BFS, it will decrease every time you visit some node. So every time you visit some node in your BFS, one value in the array decreases. Values can only decrease 2 to the 20 times 20 times. Otherwise, they'll all be 0. Okay, so that's why it's safe to do a bunch of BFSs in this array as long as we never make anything bigger. So our runtime will only be 2 to the 20 times 20, which is small enough. Okay, so now what do we do from there? Yeah, we're gonna consider like a certain thing, basically. So we're going to brute force what this endpoint is, and we're kind of gonna do a 2-pointer sweep. So here's the idea. When we have some permutation like this, if we did all of these swaps in this order, we did all of these swaps to the value that we start with, to our original bit mask. And then we have some target bit mask too, right? We would have to undo these swaps in this order. So if we do all of them like this and then undo them like this, that would be the goal. Alternatively, we could do all of these swaps like this to the starting mask we're given. And then instead of changing the mask that we get after we do all of these, we can imagine reversing what the target is. So in this case, we could undo the target in this order, I'm pretty sure. So in this way, we're kind of doing like a meet in the middle. We're brute forcing the right endpoint from one of the masks that we know, and we're brute forcing the left endpoint from the other mask. So if you do all of these operations to one of the masks, and then you do these operations to the other mask, we just want to see like what is the minimum distance, basically. So we have a bunch of nodes that we can reach. All of the start nodes will be, you can reach any prefix here. So empty, you could reach, that's going to be some start mask. We have the start mask, we do nothing to it. That's some start node. We also could have the start mask and do one swap to it. That's another possible start node. Then we could have the start mask and do 2 swaps to it. Now we have some third possible start node. So here are the 3 possible start nodes in this BFS. We want to say, what's the shortest distance to this node here? Assuming now when I say this, I mean like you have this, you do all of these changes to it. And then that'll leave you with some binary mask. So now in order to change this, we have to be able to do 2 types of modifications. The first is we have to be able to add a new mask here. We have to see if we add one more swap to the start nodes, what mask will we get? And then we can BFS from that. We can add that to our start nodes for a BFS. So to do this, this is really easy. Assuming I've got this order right, it's really easy. All you need to do is just do a swap to the mask. We can maintain the mask, do another swap, that's easy. The slightly harder one, which still isn't too bad, is we have to like add one more thing from this starting mask. So this is the ending mask that we're modifying. This is the starting mask. We have to say, okay, do everything you just did, except before doing all of those swaps, do this other swap. Now, that's not actually that hard to do either. The reason for it is that, let's just look at this as a permutation. So if we have some permutation of how these bits get permuted, then we just do some other permutation before that. We can compose 2 permutations in linear time. So adding this will just be an order 20 thing. And then to figure out what the actual mask is, we can just iterate through every bit in the permutation and see where does this correspond to the original value of. That would also be order 20. So that's plus order 20. So the final runtime is just each time we want to add something, it costs 20. And then we also do our BFS. The final runtime for the BFS is 2 to the 20 times 20. So the final runtime, for a bunch of reasons, is 2 to the 20 times 20. Maybe like times 2, kind of, if you count that. So that's the general idea. It's a little tricky of a problem to explain, but hopefully that made sense. Okay, yeah, that's all of the problems I don't know how to do. The next one, I imagine it's some sort of, like, you can do a naive DP. Maybe you can do math to speed it up. Like, you can do some DP with math, and that works. But maybe, yeah, like, that would be too slow, I guess. So you have to be smart in order to make this go faster. I don't know how to do problem I just didn't get there. Alright, that's all from me. I hope you enjoyed the problem set as much as I did. I certainly enjoyed solving the problems. And, yeah, good job to the writers. There will be an algorithms thread coming out in just under 2 hours, or it'll probably be about just under an hour by the time this gets processed, because it's going to be a very long video. Since the contest was 3 hours, plus there was like 45 minutes of tutorials afterwards. So, yeah, this will be out in maybe 45 minutes, I'd say. Which means about an hour from now, there will be Algorithms Thread Episode 8 coming out. So if you're new to competitive programming, like if you didn't solve A through D easily, I'd say it might be something worth watching. So watch out for that. That's all. Thanks for watching. Have a great day, and goodbye.